Good evening, everybody. This isn't a technology problem. I wish I could brush it away as simple as that. I put my presentation, which I presented to the U3A group over in England last summer, uh, in my bag. I checked it. I double checked it before I left England to come here. And I put plugged two of them in, and it's not there. So we managed to find a presentation which I've never seen before. So I don't know what the next slide's going to be, but it does cover the Vera Rubin telescope. And especially those of you who are beginners to astronomy might find this fascinating. I don't know what's going to come up in each slide, but I hope I get over to you why this is so totally different to anything that's ever gone before. It's unusual in the sense that it's going to be scanning the sky for the next 10 years. It took its first light in other words, the first processed look at the heavens in June last year. And it's got a 10-year program. It'll probably run on much longer than that. And the biggest difference is the camera that's attached to it. I think all the telescopes, including the astronomical telescopes, including the South African Large Telescope, Sutherland, including all the big telescopes of the world up in Hawaii or Chile, they are astronomical telescopes. They're gathering in light. Even the James Webb Telescope, it gathers in light and then concentrates it down to some form of camera. I think what we're going to talk about this evening is the fact that, in my view, this is the other way around. And they all take, if you like, still pictures. The Vera Rubin telescope, I'd better to call it the Vera Rubin camera. So it's far more like the biggest, humongous digital camera, movie camera that's ever been made with an astronomical telephoto lens put on the front of it. And that is the big difference. And that's the nature of its mission. As it says there, it's going to take an incredibly wide view, ultra high definition, time lapse. Basically, I think they're taking pictures every 4 minutes of the sky and then digitizing it. And as it says there, I mean, I've not seen this slide before, the greatest Cosby movie ever made. I couldn't give it a better term for that. So again, I'm looking at these slides for the first time as well. Vera Rubin was a trailblazer. I did read some more about her. When she became involved heavily in astronomy, women just were very much frowned upon. But she really did break through enormously. And she, as it says there, came up with some convincing evidence, which has been developed and built on since, of the existence of dark matter, which has always been a controversial subject. Still not firmly established, but it's the general view of astronomers at the moment that it does exist. And so the telescope was named after her. It's in Chile at the top of a mountain, and that's a pretty good picture of it. Funded by a number of different countries. Very, very high up. For those of you who are beginners again to this topic, there are a number of places which are very, very popular for clusters of telescopes. Chile is one of them, near the Atacama Desert and up in the mountains, because of its incredibly clear skies, lack of rain, low humidity. Much the same as in the Australian outback, and of course here in the Karoo, where the South African Large Telescope is located. So that's where it's located, and I think it's about 11,000 feet up. So there are a number of other other observatories around it, but they're traditional observatories, nothing like this one. So what's the difference? First of all, magnification doesn't come into it. Whenever one thinks about astronomical telescopes or whatever you're going to buy for yourself, how much does it magnify? Magnification is not important to this because of the incredible sensor that's picking up light over a very, very wide angle at periods of a few minutes and through different color filters as well. So it's going to be tracking the southern sky. Now, the thing that Hawaii and then certainly Chile, South Africa, and Australia have in common is that they're in the southern hemisphere. Now, I don't know how many of you are familiar with the northern hemisphere stars. I remember when I first came here, it was all new to me to see the southern hemisphere stars. But the fact is, our center of our own galaxy is in visible in the southern hemisphere. It is barely visible in the UK, barely rises. It's in Scorpius and Sagittarius. So this view of the concentration of our own galaxy, let alone way, way beyond there, is always an advantage for the southern hemisphere. It is a discovery machine. It is absolutely incredible, as it's looking at everything basically, because it's taking a most unbelievable high resolution picture. And I'll explain that and get you to compare it with your own cameras at home shortly. I'm sure it's going to be on here. It's tracking anything in the sky. And as it's tracking it every few minutes, and it's going to be doing it in chunks of the sky over a 4 day period, and then it starts all over again, does it for 10 years. Now, I call it a movie camera. Okay, we need 30 frames to 50 frames a second for the human eye with our normal movies. But really, with astronomical timescales, something that's done every few days is just an absolute instant, less than a blink in time. So it really is a movie of the sky. And it's going to be looking for everything. And I'm sure it's going to be on here. On its first day that it looked at the sky and it published them worldwide, a number of photographs, it made some amazing discoveries on its very first day. So I'll tell a lie. It's not every 4 days. It's every 3 nights. Sorry about that. I'm trying to use my brain. Wide field. Most astronomical telescopes, you're looking at a very narrow field. And it has it has 6 different color filters. So it can break down, do almost a bit of spectroscopy on this. So they call it the LSST. It's going to be the most detailed time-lapse view of the cosmos ever generated. And that's absolutely true, because everything else is built up over periods, of days, weeks. If you go right the way back to, and you're going to use that same technique, those of you who, know a little bit about your astronomical history, when Clive Tombaugh in 1930 discovered Pluto, he was using the traditional method of the flicker. In other words, he had a picture of an area of sky where a suspected planet 9 might be, and he had one a few days later, and they looked for a flicker of light, which would indicate something has moved. And this is using the same thing, but instead of using it for one object, it is looking at the same time at billions of objects. So come to the amount of data that's collected afterwards. So its first look, right? So you can see there the telephoto lens stuck on top of the world's biggest digital camera. This is one of the first day pictures. I think it's one of the star fields. Now, my thoughts on this, why is it watching to see things moving? Well, those objects there, anything in the near ground, are likely to be in our own galaxy. But some of the other photographs that are taken, we're getting a bit further away. We're seeing galaxies, and many of those objects out there are galaxies. Now, if you just to make us all feel sufficiently frightened, one of those tiny little dots, the very, very faint dots, you can barely make out. And then 4 days later, that tiny little dot has moved. We may be looking at a rock in our own solar system that's hurtling, that never been seen before, because of the absolute incredible resolution of this phone. When you use your iPhones and you start to swing out with your fingers, you make about 4 or 5 times, start to expand out. You get to the original photographs, you're saying they're digital, and you can be enlarging and enlarging and enlarging. It is quite incredible. The amount of detail and the file size of these is incredible. When those that they published. This, I think, was a whole load of in the area of the Virgo cluster. In the constellation of Virgo, there's a cluster of galaxies, and we call these our local galaxies. And I know Richard will probably know how many light years away the average is, but it's probably measured in tens of millions of light years, probably. This first picture, the one in the middle there, saw that trail goes back about 55 million light years, and that had never been noticed before. Just seeing trails of galaxies, completely unaware, attached to our own galaxy and that string of galaxies in Virgo. Again, these are incredible. These are all first day photos, and they were in my original presentation. And in fact, this is better because they can actually say the bit of sky they've got them for. So there's star fields there that are local. There's galaxies which are, measured in tens of millions of light years away. Then there are dots, which are probably other galaxies which are hundreds, if not thousands, of millions of light years away, billions of light years away. And some of those little dots, which you can't tell straight away, might move and might be a piece of rock hurtling in a dangerous direction. And no one's ever been able to do that before because it is done as a movie. So asteroids, see, yeah, can you see little lines there? That's in, I've not seen this photo before, but I can I see they're getting at. I'm talking about little bits of rock that might come our way, but already it is seeing movement. Those little lines are movements in the different color filters that it's used are asteroids in our own solar system. Some of those may not have been known or discovered before. Don't know what that is. So these are the areas of which it's going to be concentrating on over the next number of years. Our own Milky Way structure, the formation and structure of our own galaxy, because we'll be getting views, particularly through some of the filters that be able to, possibly if it gets into the infrared as well, we'll be able to see through the dust lanes of our own galaxy, to get more evidence for the existence of dark matter and dark energy, to controversial but being more readily accepted in recent years into accepted thought that they do exist, although the actual evidence, the mathematics of it, still have not been established. And then looking at the night sky and how it's changing at a minute level. Figure that out. 10 million movements in a single night it's going to be detecting and has detected in the first night. Now, some of these changes, not only just changes in movement of the object, but every single little dot that you saw up there, the Vera Rubin telescope is recording also its brightness and possibly through the filters getting some idea of the color makeup of it to get some idea of what it is. Now, I assume this is going to come onto it afterwards, but the actual amount of data is colossal that it's collecting every night. It's measured in petabytes, so we're talking about 10 to the 15 bytes per night. It's a colossal sum, and that can't be processed easily on one computer. I remember sitting here for a talk when they were talking about the SKA, which still hasn't come online, but they were talking about the plans for it, that when they were planning for it, again discussed in this very room, that there was no computing power available in 2015 to process the amount of data that's going to be coming through. There is now disk storage, cloud storage. It is colossal, but it wasn't then. But they knew they were going to collect it from the SKA. Likewise from this. So what they've done is they've set up 9 processing laboratories around the world, one of which is in Edinburgh, which will actually collate bits of this data and start to get the patterns being put through and reporting them. See if they measure it. So there we go. Just have a look at what it's saying there. Nightly alerts. Any alert will be, there will be millions of alerts each night. It can be a sudden burst of brightness. We know that in our own galaxy, supernovas is pretty rare. There's been a couple recorded in the last 1,000 years, supernovas in our own galaxy. But what Vera Rubin discovered on its very first night was there are supernovas popping up all over the universe all the time in a staggering number of galaxies that are out there. And what's the figure it's got there? 800 images for each of the areas that it's looking at for 10 years. So to be able to map timescales. So you see, this is quite different to any other form of telescope that's ever existed. Supernova, black holes, anything like that, will be able to detect what's happening. That lead in, for those who've been following the recent announcements, it was 10 years ago that gravitational waves were discovered, which was theoretically put forward by Einstein and actually discovered that they exist 10 years ago exactly. And they'll be able to see things that occur that could cause like a colliding black holes, colliding neutron stars that cause these gravitational waves. So look at variable size, a number of other things there. I don't want to just read what you can see there. as it says there, looking at things that are lasting for years, stars that flare up for many, many years, emerging neurostars. I apologize if I actually say something and it comes up on the screen. I don't know what's coming next. But neutron stars are incredibly dense stars. They're sort of one level before you get any more condensing, it becomes a black hole. Incredibly heavy. Again, mapping our own Milky Way in 3D. I'm waiting here, so I wanted to talk about the camera. So it's going to map 20 billion stars. Can you imagine that? 20 billion stars, its brightness, its position, its color, every 3 days. Incredible. So galactic structures here. Dark matter. I'm pushing on because I really want to talk about the camera. Gravitational lensing, you can see. Anyone, well, for those of you who don't know what gravitational lensing is, one of the theories of Einstein's laws of relativity pointed out, I don't remember if it's general or specific, was that heavy masses can bend light. In other words, space is curved. And we have observed for quite some time now that you often see in some photographs pictures of galaxies, not like that, like a hexagon or octagon around something in the middle, dark spot. And that's a gravitational lens. Basically, it's the same galaxy, but the light's been bent round a very large mass in space, way out. And that, again, was another one of the proofs of Einstein's laws of relativity. Clusters of galaxies, I talked about that. They saw strands going back of our own local galaxy cluster, never seen before, didn't realize it. Supernova, they're just massive. That's quite something. We know that at the edge of our own solar system, we have the Kuiper belt, and then there's the Oort cloud. And in the Kuiper belt, there are lots and lots of objects. Some of the comets that come loose just come hurtling our way. And it's a toroid, if you can see a donut shape around us. And it's going to try and map it for the very first time. Previous telescopes would not have been able to actually, they may have picked up some of the objects by brightness, but not by the movement of each of those individual components. So how the planetary systems formed. So there are lots of areas they're researching. Now, things that are coming from outer space, the things that we'd rather not think about. Another talk I give at the U3A is basically how long can life exist on Earth? And one of the things we think about is in astronomical terms. We know that a massive object hit the Earth in 66 million years ago and saw the end of the dinosaurs. How frequent do they arrive? And where do they arrive from? And I would recommend that if you get onto Google and Google Chelyabinsk in Russia 2014, you'll see that something came and just missed that city, just grazed the top of it. And it's all the photographs are taken by street cameras and dash cams in cars. And it just blew out windows, the sonic bang, but it landed it was in February 2014. It landed in a frozen lake, burnt up a lot. But the hole was still a meter wide. It was probably 30 meters wide when it entered the Earth's atmosphere. So things like that can cause problems, which asteroids might fall for as a problem. So again, they're looking at other aspects which I'm really not too well up on. I want to talk about this camera. LSST camera. Here we go. The camera. How many of you got digital single lens reflex, DSLR? How many megapixels is it?
Old model, 9 million.
9 million. So fairly modern ones, Nikon or Canon, 25 million. There are some up to 50 million. This camera and its blue thing up there, it's sensor, 3,200 million, 3.2 billion megapixels. It's just unbelievable. Now, I don't know if we're going to have this on one of these slides, but on my presentation, I did have a picture of a person holding a mock-up of the actual sensor. And we know that in our own cameras are about that big, you know, for a 35mm. This thing is colossal. You know, literally, this is a sensor, 3,200 megapixels, 3.2 billion pixels, 45 times the area, and the 6 color features front and back. So you get the point I make about the fact that this is a camera, and it's a movie camera in astronomical terms, very frequently, every 3 days, pictures everything. Colossal amounts of data. Every tiny little faint dot that you saw in those photographs will be recorded somewhere for its exact position, its exact color, its exact brightness, and any changes that get made. It's colossal. Yeah, the camera, the actual telescope itself has a strange arrangement of mirrors and lenses. You can see it there in the picture. Unfortunately, it takes a lot onto the primary mirror, but the primary mirror has very, very large hole. It reflects up to the down and then back up again into the area where the color sensors are for the doing the filtered, all the different taking pictures of the same area of sky, but through a different color filter. I was wrong about that. No, I was right. So a 32 megapixel image every 40 seconds. Figure that in your camera. 20 terabytes of data every single night. That's 20 times 10 to the power 12. Bytes of data have got to be processed every single night. 500 petabytes, that's 500 times 10 to the power 15 over that 10-year period. And it's just trillions and trillions and trillions of measurements of billions of objects, all through that massive sensor. And here's the network put together. You can see the one up in Scotland. So they spread it around and try to get people to process parts of it. So alerts are made, and an earlier slide said this. They are receiving, and this goes right from day one, that analyzing the data that goes through, up to 10 million alerts a night. Some of these are mundane, but it could be anything. It could be something has moved slightly, something has changed its brightness slightly, something just a whole series of criteria. But that's an awful lot of data to analyze to come up with these 10 million alerts. Then you've got to filter through the alerts, which are the important ones. Billions of objects measured hundreds of times. So they've got their, you know, not surprising they have to use a lot of algorithms. Whether they use AI, I don't know. In my mind, AI sometimes stands for artificial idiocy, but, you know, that's it. So you're looking for the rarest of rare events, which would otherwise be not seen at all, because traditional astronomical telescopes go to areas. The way things work, including the South African Large Telescope, all of them, they have areas of the sky that university researchers want to see, and for that period of the night, it will slew to it, look at it, put in various filters that's requested, and the university will get its get its analysis and leave them to do it. Here they've got to do all the alerts themselves and then fly this out for everybody. Leave me to read that. I mean, the figures are just staggering. 10 million alerts a night to something. So these are the community brokers. These are the areas in different sites where they're actually passing things out to. This is more of a commercial slide. Annual data releases. So they're going to catalog everything, but obviously it hasn't been running for a year yet. So it'd be interesting next June, coming June, when they start to actually do publish. Strangely enough, the pictures that were on this, same pictures I had on my own created one, which were all taken on day one. They haven't published a lot of public photographs since then. So it's going to be very interesting, because the photographs aren't interesting. What's interesting are where they've seen the movements. Let's see that one. Public outreach. 10 million alerts sent to your mobile phone. I don't know. That's an interesting statement, isn't it? Again, this is first sight to me. Don't shoot for the stars. We already know what's there. Shoot for the space between them, because that's where the real mystery lies. And that's true. That's the answer to dark matter, dark energy, certainly. So I think, thank you very much for finding this one publicly. I'm humiliated by leaving my own one at home, but this was a very, very good one. And I hope you found it interesting. So it just matches up with the point I want to make. Why is it so different, which we put in the publicity? All the telescopes in the world that you know of are big, big telescopes going back from Palomar, Yerkes Observatory, through to the Hubble telescope, through to the James Webb telescope. They are telescopes that are concentrating light down into a camera. This is the other way around. This is a dirty, great video camera with a massive field of view with an astronomical telephoto lens stuck on the front. That's the way I see it. And this is what's happening. The amount of data that's being collected is just mind-boggling. And thank you very much for your time.